The sections 4.7 and 4.8 in chapter 4, they are pretty easy and straightforward. So we are going to discover how to find a basis for row space, column space, and null space of a matrix. We will see what it is. And also we will discover what is rank and what is nullity of a matrix A. So a couple of definitions, but mostly we will have some very useful results and very easy way to find the basis for row space, column space, and null space. This is also going to help us find a basis for a span of certain number of vectors. We are just going to form a matrix with those vectors, put them in columns, and then try to find the basis for the column space of a matrix. So that will be our strategy. It's pretty easy actually, so I hope you will enjoy this. Couple of definitions. So if we have a matrix A, obviously we have rows and columns. So columns form a linear space, which is span of the columns. So it's linear space created by all linear combinations of columns of the matrix. That space is called column space of A, noted like this, col A. So that's nothing special, it's just a column space. You see that each column has m components, m entries. So the column space is a subspace of Rm. An interesting thing is we have been solving Ax equal b for a while now, and now when we have a definition of column space of A, this means that the system Ax equal b has a solution, one or infinitely many, if and only if B is actually a linear combination of columns of A. So B belongs to column space of A. In that case, the system will have a solution. If B does not belong to the column space of A, well, the system does not have a solution. This is just an observation. Just because we introduced a new definition, then we realized that we can use this as a new knowledge, but nothing special. This is not going to help you actually solve the system, by the way. This is just one extra notion that we have now. Rows, they can form a linear space also. So row space of A is a linear space that you get by all linear combinations of rows of the matrix A. So you see every row has n entries, so row A is a subspace of Rn. And the third space related to a matrix is called null space of a matrix. Sometimes it is also noted as kernel of a matrix. I will use the notation null space, it's just easier. So what is null space of the matrix A? So I have my matrix. Well, null space is defined as the space, linear space, of all solutions of the homogeneous system Ax equals 0. So we have our homogeneous equation. We know that it has at least one solution always, x0. Maybe it has infinitely many. So the set of all solutions of Ax equals 0 is actually a linear space, and the name we give it is null space of A. And obviously it is a subspace of Rn because we have n columns and X has n entries, so null space will be a subspace of Rn. Just an observation again. To find the basis of this null space, we will need to solve Ax equals 0. We will see how to do it. We know how to solve it, it's not a big deal. Dimension of the null space, so dimension of this special space, is called nullity of A. So it's just another name to remember, or just dimension of the null space. It's up to you if you want to remember one more name, nullity A. This, by the way, corresponds to a number of free variables in the equation Ax equals 0. That's something we are going to see again. So null space is just a space of solutions of Ax equals 0, nothing else. Couple of interesting observations. We remember that matrices A and B are equivalent when we can start from A and apply a certain number of elementary row operations and get to B. Okay, so we can go from one matrix to another using elementary row operations. Then we say they are equivalent. So when we are solving, let's say Ax equals 0, when we are applying elementary row operations, each new system, each new matrix is equivalent to the previous one and to every other matrix. So our elementary row operations are producing a sequence of equivalent matrices. Now the good news is that the row space of two equivalent matrices is the same. Even though the matrices are different, the row space is the same. This will be extremely useful to us. And also the null space is the same. For the null space we know kinda because we are solving Ax equals 0 and the solution space is preserved. So this one we expected that null space would be the same and row space is also the same. But column space is not. Column space is very dangerous. It's not the same at all. So now we introduce a new expression, rank of A. Rank of A is just a number of linearly independent rows of a matrix A. So we count how many linearly independent rows we have. So we just check the dimension actually of the row space. But very important result, number of linearly independent rows of A is the same as number of linearly independent columns of A. So that's something that we are going to use a lot. That's a very good result. So that's why we say that rank of A and rank of A transpose is the same number, because we have the same number of linear independent rows and linear independent columns. So that means that the dimension of the column space of A is the same as the dimension of the row space, because we have the same number of linear independent rows and same number of linear independent columns. Another observation, when we are solving Ax equals 0 homogeneous equation, rank corresponds to the number of leading or main n variables. The nullity, dimension of the null space, is the number of free variables in the equation Ax equals 0. So you see there's a link between rank and nullity of A. So rank is number of main variables or leading variables, and nullity is the number of free variables. So when we add them, we get the total number of variables. There's a theorem about that. Some more equivalent statements, but these are for square matrices. So again, we recall that rank is just a number of linearly independent rows of a matrix A, which is the same as number of linearly independent columns. So when my matrix is square, we will say that rank of A is n, and then we have all these equivalent statements. When we say that the rank is n for n by n matrix, we will also say sometimes full rank. A has full rank. So when rank is n, that means that I have n linearly independent rows and n linearly independent columns. But this is equivalent also to saying that the reduced echelon form of matrix A is actually identity. Oh, when that happens, we remember from equivalent statements, that means that A is invertible, which means determinant is different from 0, which means Ax equals 0 has a unique solution x equals 0, which means that Ax equals b has also a unique solution. So all these here, we already know them. Those are equivalent statements. The only new thing is, we said now we have rank. Rank is number of linear independent rows and linear independent columns. Well, we have a new comer in the equivalent statement sequence. Just to specify, when I have a square matrix and I'm solving homogeneous system x equals 0, this system will have infinitely many solutions if and only if rank is smaller than n. Rank is number of linear independent rows and columns. Okay, n is total number of rows and columns. So if the rank is smaller than n, then we will have infinitely many solutions, because then we have at least one row in our reduced echelon form that will be 0. So we will have more unknowns than equations, so we will have infinitely many solutions. Okay, but when the rank is full, when rank is n, then we have a unique solution. So this is just another translation. When rank is n, that means that all rows of matrix A are linearly independent. So they are vectors in Rn, so we have n vectors in Rn that are independent, which means all rows of matrix A will form a basis for Rn, which means that actually span of all rows, which is called the row A, row space of A, is actually Rn. Wow. But a matrix has the same number of linear independent rows and columns, so if I have n by n that has n linear independent rows, it has n linear independent columns, which means that now the columns are also basis for Rn, which means that span of the columns, which is called column space of A, is equal to Rn. This means also that our matrix is invertible and Ax equals 0 has a unique solution. So the null space will only be a vector 0. Right? Rank n means matrix invertible, Ax equals 0 is the only solution is x equals 0. So the null space will be just vector 0. So all these things are equivalent statements. We need to remember this because it's very useful. The theorem that links the total number of variables, so it links total number of variables with rank of A and nullity A. If we check what it is actually, so this is a rectangular matrix, so we have n variables, so total number of variables is n. We separate them in two groups, leading variables and free variables, right? So number of leading variables, that corresponds to rank A, plus number of free variables, number of free variables is equal to nullity A, dimension of the null space. Well, when we add them, we have all the variables, so total number of variables. So this is very nice result, very useful. We need to remember this. So total number of variables is equal to main variables, so number of main variables plus number of free variables. That's it. So dimension of the null space is just, remember, nullity. So that's equal to the number of free variables. Rank is equal to the number of main variables. Rank tells you how many rows are linearly independent in matrix and how many columns. So this result is very important, so we need to remember it. It's very intuitive, by the way, also. An application of this result. So let's say I have a matrix 7 by 9, so I have 9 columns, so 9 variables. And the question is, I have this matrix 7 by 9 and its dimension of its null space is 2, two-dimensional null space. So nullity is 2. What is the rank? Well, that's not complicated because the rank plus nullity is equal 9. Rank plus nullity is equal 9. Like nullity is 2. 9 is total number of columns or variables as you like. So rank must be 7. Very easy. Another question, if I have 6 by 9 matrix, okay, so that means I have 9 columns or 9 variables if you wish. Could a 6 by 9 matrix have a two-dimensional null space? Two-dimensional null space means that nullity is 2. Dimension of the null space is 2. But we remember that the rank plus nullity is equal to 9. So if nullity is 2, then rank needs to be 7. But wait a minute, I have only 6 rows. Rank equals 7 means I have 7 linearly independent rows and 7 linearly independent columns, but I only have 6 rows. So this is impossible. So it's not possible for a 6x9 matrix to have two-dimensional null space, obviously. Right? Rank plus nullity is equal to total number of columns, total number of variables. You see here I have 6 rows, so I cannot have 7 linearly independent rows. I only have 6 rows. Now the big question is, how do I find a basis for all these spaces, row space, column space, and null space? We will see this is super easy, straightforward. So the first thing we need to do is take our matrix A and produce echelon form. Or, if we are very persistent, we can produce reduced echelon form. Okay, any one of the two will work. How do we do it? Well, using elementary row operations. So we have equivalent matrices. So all the non-zero rows of echelon form or reduced echelon form, whichever one you have, doesn't matter. So all the non-zero rows of echelon form or reduced echelon form, they will create a basis for the row space of A. So it's very simple. You get your echelon form that has all your 0 rows at the bottom. So all you are checking is non-zero rows. You take all of them, they are basis for row space of A. Very simple. For the column space, it's a bit more complicated and touchy, but not too much. So I have my columns of A, but I have also columns of echelon form or reduced echelon form, whichever one you have, it's fine. So what I need to do is locate the pivot columns of A, the columns that have the leading entries, okay, in my echelon form or reduced echelon form. And then the corresponding columns of A will be basis for the column space of A. So that's a little bit more complicated than the row space, the basis for the row space, because here we need to get our echelon form and then locate the columns containing leading entries. The corresponding columns of A will form a basis for column A. We will see a couple of examples for that. Okay, so that's not complicated, but more involved than row. For the null space, to find the basis for the null space, we need to solve Ax equals 0, which is the same as solving Ex equals 0. So this is echelon form, or Rx equals 0, reduced echelon form, whichever one we have. So we need to solve, we have no choice. So to find the basis for the null space of A, we need to work. For row space and column space, it is quite easy, because all we need is echelon form or reduced echelon form, whichever one we have. But for the null space, we absolutely need to solve Ax equals 0 or Ex equals 0 or Rx equals 0, whichever one we have. So what we know is that row space of A, E, and R is the same, because A, its echelon form E, and its reduced echelon form R, they are equivalent matrices, row equivalent. So they have the same row space, and they have the same null space. So we know that. But they don't have the same column space at all. So be very careful. Column space of A is not the same as column space of echelon form or reduced echelon form. This is super important. Row spaces are the same, null spaces are the same, but column space is different. To get the basis for the column space of A, we need to go back to the matrix A. Okay, an easy example. Here I have a 2x2 matrix, and I check this, so I have 2 columns. Well, they seem to be linearly dependent, because column 2 is just 2 times column 1. Wow. So how many linearly independent rows or columns I have? 1, because the other one is dependent. So I have 2 rows And if you check row 2 is 3 times row 1. So I have one linearly independent row, so the rank is 1, and I also have one linearly independent column, obviously. And from the rank plus nullity theorem, I know that rank plus nullity is equal to number of columns. Here number of columns is 2, rank was 1, so nullity must be 1. So I have that immediately using the theorem. Immediately, very simple. So what is column A? Well, basis for column A is the first column. I just need one of them because I here only have 2 and one is dependent, the other one is independent. So I need one of them. So this is a basis for column space of A. So column space of A is span of the vector 1, 3. Similarly for the rows, I only have 2 and they are dependent, so I pick one. That one is a basis for the row space of A. You see, I don't need necessarily to produce echelon form here or reduced echelon form. I could, it's just one operation, but having only 2 rows and 2 columns, it makes things super easy. Null space, well, I need to solve AX equals 0. I need to solve this, no other choice. So solve AX equals 0, it's not a big deal. Once you finish, you get a result like this. So you have a scalar multiple of vector -2, 1. So basis for the null space is this vector here. Okay, so null space is span of the vector -2, 1. Because the general solution of AX equals 0 is this. It's a multiple of the vector -2, 1. So this vector is a basis of the null space. And the null space is all scalar multiples of this vector. So if you do actually A times this vector, you'll get 0, obviously. So this case was super easy because it was 2 by 2 and everything was obvious. So we didn't even need to produce echelon form or reduced echelon form, it was easy. But it's not going to be always like this. So let's say I have a 3 by 3 matrix here, A. Now it's more complicated. I don't see anything here. So I'm going to work and produce reduced echelon form. Well, it's here. Wow, reduced echelon form is actually identity 3 by 3. Well, that's very good news. What does it mean? It means that the basis for the row space of A, which is the same as row space of R, are all the non-zero rows of reduced echelon form. Well, this row, and this row. Cool. But this also means that all rows are linearly independent. And I have 3 of them, so all 3 of them are independent. Ah, cool. So also the columns, so column 1, column 2, and column 3 have the leading entries. So column 1, 2, and 3 of A are basis for column space of A. Obviously, fine. So I have the same number of linear independent rows and same number of linear independent columns. It's always the case. So that's called the rank. So here rank is 3. I have 3 linear independent rows and columns. From our theorem, rank plus nullity, we know that nullity is 0. That means that the null space has only vector 0 inside, nobody else. And our matrix A is obviously invertible, reduced echelon form is identity. Or you could compute the determinant also of A, it's going to be different from 0, but there's no need. Since the reduced echelon form is identity, we know that the matrix is invertible from our equivalent statements. If matrix is invertible, then AX equals 0 has only one solution, X equals 0. So that's why our null space is only vector 0. So that was easy. Now, the fact that our rows and columns, all 3 of them are linearly independent and they are vectors from R3. Well, we know something from the theory. When I have 3 vectors with 3 components and they are linearly independent, they automatically form a basis for R3. Aha! That means that span of the columns, which are independent, is equal to R3. But span of the columns is called column space of A, call A. So col A is equal to R3. But also all the rows are independent, and there are 3 of them with 3 components. So they form a basis for R3 also, and they are basis for row space also. So row space is actually R3 and column space is also R3. Well, this is a miracle. Some examples of basis for row space and column space, which is also a basis for R3 in this case. So this is just a bonus actually, because we had the square matrix, its reduced echelon form was identity. We know now that all rows and all columns are linearly independent. This is a square matrix, so we know that here in this case 3 by 3, all the rows form a basis for R3, all the columns form basis for R3. Column space is R3, row space is R3. It's just fantastic. Here another example, this time more complicated. I have a rectangular matrix, 5 rows and 3 columns. Okay, well, we applied elementary row operations, we got reduced echelon form here. So from the reduced echelon form, I see a bunch of rows of zeros, I ignore those. So to find a basis for row space of A, I come here and I take all non-zero rows of reduced echelon form. That's it, finished. I don't take rows from A, hello, I take rows from echelon form or reduced echelon form. Only non-zero rows. Take all of them from reduced echelon form, puff, that's the basis for the row space of A. That's it, finished. Don't touch matrix A. You come and take it from here. That's how we do it. So since there are only 2, they have 2 linear independent rows and 2 linear independent columns, obviously rank is 2. From the theorem rank plus nullity, I know that nullity is 1. The dimension of the null space is 1, which means there's only one vector that generates the entire null space. Good. So how about finding a basis for the column space of A? Well, the theory says go to your echelon form or reduced echelon form and locate the columns containing leading entries. So here, first column has a leading entry and second column has a leading entry. This column doesn't. So column 1 and column 2 have leading entries. The corresponding columns of A, so column 1 of A and column 2 of A, are linearly independent and they form a basis for the column space of A, period. So I go back to matrix A and take column 1 and column 2. That's the basis for column space of A. Finished. Very easy. So to find basis for row space of A and column space of A, it's very quick if you have echelon form or reduced echelon form. For row space, it's easy. You take non-zero rows of the echelon form or reduced echelon form. Finished. Rank, you just count how many of these rows you have. That's your rank, and you use the theorem rank plus nullity equal, in this case, 3 to find the nullity immediately. Also, for the column space of A, you just identify the columns in echelon form or reduced echelon form that have leading entries. Here, column 1 and column 2. So then you go to matrix A and take column 1 of A and column 2 of A. That's the basis for column space of A. Finished. Bye. Now, we need to find a basis for the null space. Well, to find a basis for the null space, we must solve a homogeneous system, Ax equals 0, which is the same as solving Rx equals 0. So we can solve Rx equals 0 immediately. Just solve it properly, in details, properly. Don't mess up here. This is the only place where you need to work a little bit. Everything else is straightforward, but this place you need to work, so be careful. Spend 2 seconds extra just to make sure you don't make errors here. So you solve it, and we have scalar multiple of vector 3, 2, 1. So the basis for the null space is vector 3, 2, 1. Ba-bam, finished. But we needed to solve. So that means that A times this vector will give 0, obviously. So that's it. Very simple. Now, we need to observe something regarding the columns. Because this technique with the columns, I could just give you 3 vectors, which are these 3. You could create this matrix out just by yourself, it's fine, and apply elementary operations, get reduced echelon form. And then you say, oh, column 1 and column 2 are linearly independent. True, fine. That means that column 3 is linearly dependent on the other 2. So that means that column 3 is linear combination of columns 1 and 2. Yes. But what are the coefficients of that linear dependence? Which means that column 3 is some number times column 1 plus some other number times column 2. What are those numbers? Well, look at here. Reduced echelon form gives you that information straight for free. It tells that column 3 of A is minus 3 times column 1 of A minus 2 times column 1 of A. So here is the formula. Ta-da! So column 3 is minus 3 times column 1 plus minus 2 times column 2. Finished. So reduced echelon form gives you the coefficients for linear combination. Amazing. Another example, more complicated. I have a matrix A here. I look and I see that this matrix is already in echelon form. Well, that will simplify my life, because now matrix A is equal to an echelon form of A. So that's cool. And I check, I take all the non-zero rows, and those are bases for the row space of A. Bye. A is equal to echelon form of A, so I don't need to change anything. There's no point. I'll just take all the non-zero rows of echelon form, which is in this case A also, and this is basis for the row space of A. Easy. How many they are? 1, 2, 3. So rank is 3. Nullity, well, nullity plus rank is equal to 5, because I have 5 columns. So nullity is equal to 2. A little bit of algebra. So what's the basis for the column space of A? Check this. I need to find all the columns of echelon form, which in this case is A, that have leading entries. So that's column 1, column 2, and column 4. Be careful. Echelon form, revision, important. So here column 1, column 2, and column 4 have leading entries. Therefore, they are basis for the column space of A. Finished. Easy. Super easy. Which means that columns 3 and 5 are linearly dependent on the other 3. That's what it means. So how they are dependent? Well, I need to get to reduced echelon form for that, because reduced echelon form will give me the coefficients. So that requires a little bit of work. So column 3 and 5 are linear combinations of columns 1, 2, and 4. And here are the coefficients. For column 3, that's a linear combination of column 1, 2, and 4. And coefficients are 3.5, 1, and 0. It's 3.5 first linear independent column, which is column 1, plus 1 times the second linear independent column, which is column 2, plus 0 times the third linear independent column, which was column 4. So this tells you this is for the first coefficient in front of the first linear independent column, coefficient in front of the second linear independent column, and coefficient in front of the third linear independent column. In our case, those are columns 1, 2, and 4. For the column 5 of A, these are the coefficients of dependence. It's 1.5 first linear independent column, which is column 1, plus 0 times the second linear independent column, which is column 2, plus 0 times the third linear independent column, which is column 4. Tac, tac, tac. Simple. So that's how you get your linearly dependent columns as linear combination of linearly independent columns. Cute. Everything from the reduced echelon form. So now if I want to find the basis for the null space, I must solve Ax equals 0. Absolutely must solve Ax equals 0, which is the same as solving Rx equals 0. And since I have my reduced echelon form, from here I form the equations. Rx equals 0. Be careful, solve it properly. And here I see that I have two free variables, obviously, x3 and x5. x1, x2, x4 are main variables. We know that. So you just write your solution that has actually 5 components because you have 5 columns. Write it properly, factor it properly, and then you'll have 2 vectors. Those 2 vectors are basis for the null space of A. Bye-bye. By the way, they are basis also for the null space of R, and also null basis for the null space of echelon form, right? We know that from the previous result. Another example, again the same strategy. Here again I have a rectangular matrix, 3 by 5, and I need to find basis and dimension for row space, column space, null space, and eventually linear combination of the linearly dependent columns. So I have echelon form and reduced echelon form here. Somebody worked for that, obviously. We know that row space of A, row space of is equal to row space of echelon form and is equal to row space of reduced echelon form. We remember that the basis for the row space of A, we need to take all non-zero rows of echelon form, or all non-zero rows of reduced echelon form. You choose which one you want. It doesn't matter. So basis for row space of A, I can take it from non-zero rows of E, echelon form, or I can take it from non-zero rows of reduced echelon form. My choice, whichever you choose, it's fine. Rank, which is number of linear independent rows and columns, is 2. I have 2. From the theorem, rank plus nullity is equal to 5 because I have 5 columns. Since rank is 2, nullity must be 3. Simple, straightforward. So for now I know that I have 2 linear independent rows and 2 linear independent columns in matrix A. By the way, it's the same thing for matrix E and R. They have 2 linear independent rows and 2 linear independent columns. So how do I find the basis for the column space of A? Very simple. I take echelon form or reduced echelon form, doesn't matter, and I find the columns containing leading entries. In this case, it's column 1 and column 3. They have the leading entries. Obviously, the same thing in reduced echelon form. So I go to matrix A and I take corresponding columns. So column 1 and column 3. They are linearly independent and they form basis for the column space of A, period. Do not take those guys. You see that those guys have 0 in the third component. So third entry is 0. So you can multiply by any number, you still get 0. There's no way to generate 2 out of 0. You see this guy on third component has 2. So these 2 guys cannot generate him. His third component is 2, but third component of these 2 guys is 0. So number times 0 plus number times 0 is still 0. It's never 2. So you see clearly that column space of A and column space of echelon form has nothing to do with each other. The same thing, column space of A and column space of reduced echelon form, nothing to do with each other. Okay? Be careful when we are asked to get basis for the column space of A, you need to go back to the matrix A. You identified columns with leading entries, go to the matrix A and extract those columns, the corresponding columns. That's it, finished, bye. We know already that column space of echelon form and reduced echelon form is the same, even though they don't look like exactly the same, but they're the same space, but not with column space of original matrix A. So be careful. This is just an illustration to show you that column space of echelon form and reduced echelon form is the same. So I have these two vectors that are bases for column space of echelon form, and these two guys are for reduced echelon form. So obviously the first vector is the same, so I just check the second one. So second one is linear combination of these two guys, obviously. But also him from here, it's easy, just flip on the other side, is equal to this. So this vector is linear combination of the other two. Okay, so from here we know already that all linear combinations of these two guys are also linear combinations of these two guys, and the other way around. So we know that immediately the span of these two guys is the same as span of these two guys, so that's it. We don't need to work anymore. So for the column space of echelon form and reduced echelon form, they are the same, but they're not the same with echelon with the column space of A. They are different. A has a lot of numbers, and echelon form and reduced echelon form have a lot of zeros. Okay, so column space of A is very delicate. It's different from any other column space, so be careful. Now if I want to write those dependent columns as linear combination of independent columns, it's not complicated. Column 1 and 3, we know already they are independent, so they are bases for the column space of A. So each other column of A is linear combination of the other two. So how it works? Well, column 2, we have coefficients here, is -2 times first linear independent column, which is column 1, plus 0 times second linear independent column, which is column 3, because we know which columns are independent. So it's -2 column 1 plus 0 column 3 of A. Okay, column 4, so this column here is linear combination of column 1 and 3, obviously. What are the coefficients? They are given here in column 4 of reduced echelon form. Reduced echelon form. So it's -1 times first linear independent column, which is column 1, plus 2 times second linear independent column, which is column 3. So -1 times column 1 plus 2 times column 3. That gives us the column 4 of matrix A. The last column of matrix A is column 5, and it's linearly dependent on the column 1 and 3, obviously. What are the coefficients? 3 and -2. So it's 3 times column 1 minus 2 times column 3, because column 1 and column 3 are independent. So this is first linear independent column, this is the second linear independent column. Coefficients in front are given in the reduced echelon form in the corresponding column here, 3 and -2, 3, -2. Very simple. To find the basis for the null space, again, we need to solve Ax equals 0, so homogeneous system, which is the same as solving Rx equals 0. So we have R reduced echelon form given, so we need to solve Rx equals 0. Be careful. It's not a big deal, but be careful. Write your system properly, find the correct expressions, so you know that you have x1 and x3 as main variables, and x2, 4, and 5, they are free variables. So your system has 5 unknowns. Write properly your solution. This is the only place you need to work, so please pay attention. Factor it properly. You know already that you need to get 3 vectors because nullity is 3. So dimension of the null space is 3. So those 3 vectors are linearly independent, and that's guaranteed by the process. You can check it if you wish, but it's totally waste of time. We know they are always linearly independent, and they are basis for the null space of A. Very easy. Another example. In this case, again, rectangular matrix. 4 rows, and how many columns? 6 columns. Wow. I need basis for row space, column space, null space. Go. Rank and nullity. I have echelon form and reduced echelon form. I take all non-zero rows of echelon form to get basis for the row space of A. I can also take all non-zero rows of reduced echelon form. Up to you, whatever you do, it's fine. If you are given only reduced echelon form, well, you just use that one. So you count how many there are 3, so rank is 3. From the theorem rank plus nullity, you know that rank plus nullity needs to be equal to 6 because we have 6 columns. Here, if you count number of columns, is 6, so n is 6. So rank is 3, therefore nullity will be 3 also because we have 6 columns. So this is straightforward, takes 2 seconds to do. To find a basis for the column space of A, not complicated, from your echelon form or reduced echelon form, whichever one you have, you identify the columns containing leading entries. So in this case, it's column 1, column 3, and column 5. They have leading entries. Cool. Then we go to matrix A and we take column 1, column 3, column 5. Just extract them. That's the basis for the column space of A. Bye. We observe again that basis for the column space of echelon form are the columns 1, 3, and 5 of echelon form, obviously. Or from reduced echelon form is going to be the same. So reduced echelon form is basis for the column space of reduced echelon form are columns 1, 3, and 5. And we know already that column space of echelon form and reduced echelon form is the same. That's just an observation. What is important to realize, it is different from the column space of A. So that's why you must go back to A to find basis for the column space of A. Be very careful. So now, knowing which columns are dependent, which columns are independent, we can find coefficients for linear combination. So columns 1, 3, and 5 are independent, which means that column 2, 4, 6 are dependent. So they are linear combination of the other 3, of the independent ones. So the column 2, so this column here, is linear combination of columns 1, 3, and 5. What are the coefficients? -3, 0, 0, which means -3 times first linear independent column, plus 0 times second linear independent column, plus 0 times third linear independent columns. So column is 1, 3, and 5. So it's 3 times column 1, plus 0 times column 3, plus 0 times column 5. We express linearly dependent column as a linear combination of linearly independent columns, 1, 3, and 5. Okay, so now next one, column 4. This column here is linear combination of columns 1, 3, and 5. What are the coefficients? -14, 3, and 0. So it's -14 times column 1, plus 3 times column 3, plus 0 times column 5. Ta-da! This is first linear independent column, second linear independent column, third linear independent column. So the order here is for linearly independent columns. First one, second one, third one. We know already who they are. First, second, third. Okay, the last column, column number 6, is linear combination of columns 1, 3, and 5. What are the coefficients? -37, 4, and 5. Which means that column 6 of A is -37 times column 1, which is first linear independent column, plus 4 times column 3, which is the second linear independent column, plus 5 times column 5, which is the third linear independent column. Straightforward. Pop. Everything given in reduced echelon form. All the coefficients. Beautiful. Again, if we need to, and we will need to, find the basis for the null space of A, well, we need reduced echelon form, obviously. And we need to solve Ax equals 0, which means we need to solve Rx equals 0. Again, this is R given. Solve it properly. You have your main variables 1, 3, and 5 expressed as linear combination of, or is a formula containing dependent variables or free variables 2, 4, and 6. So main variables are x1, x3, x5. Free variables are x2, x4, x6. We know already that we will have 3 of them. So just write your solution. Your solution has 6 components. Be careful because your matrix has 6 columns. Be careful. Write it properly, factor it properly. You'll have these 3 vectors. They are linearly independent. You don't need to check it. You know it. It's given. And they form a basis for the null space of A. So the nullity is 3. Number of linear independent vectors in the basis of the null space. That's also equal to the number of free variables, by the way. All that is linked. So now when we know how that works, now a tricky question. I have a matrix given here, so 3 by 4, and I have 2 vectors u and v given also, and I have 2 different questions. First one says, determine if vector u, so this guy here, is in null space of A. Okay, so that's different from what we saw before. Before the question was, find the basis for the row space, column space, and null space, and find the dimension for each of them. Okay, cool. We know how to do that. That's straightforward. But now this is different. Determine if U belongs to null space of A. And also, could U belong to column space of A? Okay, weird. And something similar for V. Determine if V is in column space of A and could V be in null space of A. What are these questions? So what does it mean actually for a vector to be in null space of A? By definition, null space of A is a space of all solutions of AX equals 0. So for the guy to be in null space, that means that the guy U needs to be such that A times U is supposed to give 0. That's the only way for U to be in the null space, because A times the guy in the null space equals 0. That's the definition. So we need to check A times U. We don't need to find the null space and blah blah blah. The definition of the null space is just people such that A times the person equals 0. That's it. So we need to see if U belongs to the null space of A. We just multiply A times U and see if the result is 0. If it's 0, well, U belongs to the null space of A. If the result is not vector 0, well, then U does not belong to null space of A. That's it. So let's check. A times U, product here, this is not vector 0, sorry. So U does not belong to null space of A. So it's not in null space of A. Why? Because the people who are in null space of A times U should be 0. If U was there, it should be 0, but it's not 0, so the guy is not there. It's not in the null space, obviously. People in null space, so Z is in null space if and only if A times Z is equal to vector 0. We know the definition. So the second part of the question was, could U be in column space of A? Oh, wait a minute. Columns, they have 3 components. U has 4 components. Well, obviously not. You cannot have a vector with 4 components in a linear space of people with 3 components. So, no. U cannot be in column space of A. U has 4 components and people in column space of A have 3 components. Hello. The other question was, determine if V, so vector V here with 3 components, is in column space of A. Oh yeah, people in column space of 8 have 3 components. This guy has 3 components. Okay, so maybe he's there, maybe he's not. God knows. How do I know? What does it mean for V to be in column space of A? That means that V is linear combination of columns of A. Okay. So I need to solve AX equal V. So augmented matrix AX equal V, If this system has a solution, then V is linear combination of columns of A, obviously. If the system does not have a solution, so it's inconsistent, then V is not in column space of A. It's very simple. To be in column space of A, you need to be a linear combination of columns of A. So what does it mean? It means that you need to solve Ax equal V. So the augmented matrix here. Well, let's solve. We worked a little bit, we get echelon form, which is here. From this echelon form, so I have leading entry, and leading entry. So all looks good, so I can divide this row by 17, I'll get 1, I can kill these two guys, that's fine. And then I'll go back here, kill this guy, and then divide by 2, everything. So I'll get the solution, that's for sure. There's no contradiction in this system. So this system is consistent. I don't know what's the solution, I need to compute it eventually, but I know that the system is consistent. There is a solution here, which means that vector V is a linear combination of columns of A, which means that vector V belongs to column A. Cool. The other part was, could V be in null space of A? V has 3 components. People from the null space have 4 because I have 4 columns. So no, this guy has 3 components. People in null space have 4 components, so this guy cannot be in the null space, obviously. So all this is useful actually to find a basis for a span of a set of vectors. So if I need to do that, it's not complicated actually at all. All I need to do is take those vectors and put them in the matrix A, in columns. So form a matrix A, and vectors that you gave me, I just put them in column. Each vector in one column, bye-bye. So I have now a matrix with proper columns there, and I can compute echelon form by elementary row operations, and I identify pivot columns of echelon form, so the columns in echelon form that contain leading entries. Well, that's good. So it's like finding the basis for the column space of A. It's the same thing. So now I have the columns with the leading entries in echelon form. Well, I go back to original matrix A. The corresponding columns of A are linearly independent, and they form a basis for column A, obviously, and also for the span of those vectors that you gave me. It's very simple. You gave me 4 vectors, I pitch them into a matrix in columns, produce echelon form, identify columns with leading entries, go back to my original matrix that contains the correct columns, the corresponding columns having leading entries from my original matrix, those are the basis for the column space, those are basis also for the span. That's it, very simple. All you need to do, just put the vectors in columns of a matrix and just do as we did to find the basis for the column space of A. Easy. If you need the coefficients of linear dependence of those that are dependent eventually, well, you need the reduced echelon form, just like we did before. But if you don't push it to reduced echelon form. Don't work for nothing. Unless somebody was nice to give you reduced echelon form. I don't know who that could be. Also, another result that we are not going to use at all. Actually, you are going to use this in differential equations. And this is useful eventually for certain proofs, but we are not doing any of those. This is just a cute curiosity. So, if I want to solve Ax equal B, either it's consistent or is not consistent. If it's not consistent, doesn't have a solution, bye-bye. But if it is consistent, so I have Ax equal B and it's consistent. Okay, cute. What I know is that the solution X can be written in a very special form. One part, Z, that actually solves Ax equal B. Okay, so A times Z is equal to B. That's what it means. And the other part is very special part. Okay, here I just took three of them for illustration. U, v, w, and c, k, p are the constants. So these guys are actually bases for the null space of A. Okay, that means that A times u is 0, and A times v is 0, and A times w is 0. A times z is equal to b. Okay, so that's very special. A general solution for ax equal b, when there is a solution, can be written in this form. One part that actually solves the problem ax equal b, and other parts that are actually belonging to the null space. Very interesting. Just an observation, nothing special. So obviously, if the linear system has a unique solution, then the only solution is x equals z. In that case, the null space is 0, so the guys u, v, w just don't exist. It's just one unique solution is x equals z in that case. Okay, fine. If the linear system is inconsistent, that means it doesn't have a solution, so all this doesn't exist. Bye-bye. So this result is interesting when we have a consistent system, so it has a solution. Then we can write the solution in this way. Okay, so this is an example with 3 people from null space. Sometimes you'll have 2, 1, 7, or none, depending on the situation. An example, so I have a matrix 4 by 6, and I have b here given, so I need to solve ax equal b. Well, once you solve it with Gauss-Jordan, 2 days later you get a solution which is given here. So one part of the solution, so you see the form, it's similar. So first part of the solution actually solves ax equal b. If you do a times this vector, you will get b. Now, the other 3 guys are actually bases for the null space of A. So when you do A times this guy, you'll get 0. A times this guy here, you'll get 0. A times this guy, you'll get 0. Just do it. You'll see. A times first guy gives B. So that's what it is. Just an observation. So when we write a general solution for a non-homogeneous system, when it exists, this is what we get normally. So now we know that these 3 guys are actually bases for the null space. Okay, and this guy just solving ax equal b. Very nice. So that's all it is. It's not complicated. It's straightforward actually, but you need to practice just to make sure you know what's going on. So here you have exercises from the white book, a list of them, a lot of them. And just go through them, it's fine, they're not complicated. And also for the yellow book, depending on the sections, 4.7 and 4.8, try to solve them. They're interesting, not complicated. And also I gave you here a couple of extra problems, some of them solved with different levels of solution, so you need to complete. So basically the question is, find basis and dimension for row space, column space, null space. So I give you a matrix, echelon form, reduced echelon form, and then you have fun. So basically this one is solved in detail. We have basis for the row space given from E or R, because we are given both of them, so we can pick one of them, pick the one you like, doesn't matter. We can identify rank as 1, 2, 3, so 3 linear independent rows, 3 linear independent columns. And from the theorem rank plus nullity, we figure out that nullity is 2 because we have 5 columns, and rank is 3, so nullity must be 2. It is easy also to identify the basis for the column space of A. To find the basis for the columns for the null space of A, well, we need to solve Ax equals 0 or Rx equals 0. R is given, so just solve it properly, don't make errors. You have 5 columns, so your solution has 5 components, so be careful. You have 3 main variables and 2 free variables, so the null space is generated by these 2 vectors. So you can just compute on your own and verify. Another example, again, condensed solution, the same thing. Matrix is given, reduced echelon form is given, and then you find the rank, nullity, basis for the row space, column space, null space. So same. Another matrix, this one much bigger, reduced echelon form given, so you don't need to waste your time, it's given already. And then from here, you figure out everything as we did before. And here are some problems that are not solved, but you need to do it. So again, matrix is given and reduced echelon form is given, and you find the basis and dimension for row space, column space, null space. And also, you find which columns are linearly dependent and which columns are linearly independent. And now write your dependent columns as linear combination of independent columns, just as we did before. You'll do that from the reduced echelon form. It's very easy. Another problem like that, everything is given, you just find the things and then express your dependent columns of A as a linear combination of independent columns. Yet another one, everything is given, matrix, echelon form, reduced echelon form. So I hope you will solve these problems and the problems from the book. This part is really straightforward, not complicated, but requires a little bit of work just to make sure you grasp everything and you're comfortable with it. So that's it. This should be straightforward thing.